Hello, yes, if you've been watching my previous videos on thermodynamics, particularly deriving these gas laws, then you are not going to be surprised about what comes up here, because we got to the stage where looking at the macroscopic level, remember we came up with our ideal gas equation, PV equals nRT, so that's relating the pressure times the volume is equal to the number of moles in a gas multiplied by the molar gas constant R. That was our 8.31 joules per Kelvin per mole, and then multiplied by the temperature. We also said off of that PV is equal to capital N, the number of particles in the gas, multiplied by the Boltzmann constant multiplied by the temperature. So that was two ways of writing down the ideal gas equation. One macroscopically, where we're looking at the number of moles, and one microscopically when we're looking at the number of particles. And from this, we were seeing, of course, that the Boltzmann constant is equal to R, the molar gas constant, divided by Avogadro's constant. Because, of course, we know that the number of particles is equal to the number of moles multiplied by Avogadro's number. So all of that is fitting together. And that's where we left one of the videos. We then set off into the world of the microscopic, and then we derived another equation, which was PV is equal to 1/3 of NMC squared. That's the average. So we got the pressure times volume is 1/3 times the number of particles multiplied by the mass of a particle, because of course in an ideal gas we're assuming all the particles are identical, so they've all got the same mass, multiplied by the average of the square of the velocities of the particles in the gas. So we've now got these three equations, which obviously on the left hand side have all got pressure multiplied by volume. So we can combine these two here and say, okay, we've got nRT is equal to 1/3 of nm average at a squared of velocity. So we've now got this, but we can rearrange this in order to, you see this bit here, this mc squared. I mean, that is giving you vibes of kinetic energy here, isn't it? You know, we've got half mv squared is our kinetic energy. So let's replace that then and say that this right hand side is going to be that we've got, well, we can also do another replacement. Let's replace that capital N with this here, this relationship between capital N and the number of moles. So we've now got 1/3 multiplied by a number of moles multiplied by Avogadro's, and then we're going to have two lots of a half mv squared essentially. So because that 2 and a half are going to cancel, so we've got the same thing going on there. Right, now we can cancel the n's because we've got a n on both sides, so we can cancel those. We also know that R is K times the Avogadro's constant. So we can replace that R, make that KNA times T, and then we can cancel the NAs. So we've got K times T is equal to 2/3 multiplied by the average kinetic energy of a particle in the gas. So we're saying now, really, if we just want to get the average kinetic energy, so our average kinetic energy of a particle is 3/2 kT. So it is purely determined by the temperature of the gas. And this is what I've been saying. It's sort of been a spoiler alert throughout all of these videos. I've been talking right from the start of thermodynamics that temperature is a measure of average kinetic energy. It's kind of been hanging in the air a little bit because, okay, I could say it because it made all of the explanations so much easier and better way, you know, it's easier to understand what's going on if you know that from the outset. But I hadn't provided any kind of justification for it. I was just saying that, I think, straight from, well, maybe even video 1, but certainly video 2 in the thermodynamics section. I kept on saying temperature is a measure of average kinetic energy. Well, now we've got to the end of these videos and we can see here, well, yeah, it definitely is. I mean, we've proved this. We've derived all of these equations. I mean, we derived that in macroscopic terms. We derived that in microscopic terms. So this is all our own work here. There's nothing mystifying about any of this. And then we said, okay, for an ideal gas, this is what's happening. This is our relationship between temperature and average kinetic energy. And it's the Boltzmann constant that is making that translation between temperature and energy. That's what it's doing. It is the conversion factor between the temperature scale and the average kinetic energy of individual particles in a gas. So it's all finally come together. Now we've got to the end of all of this, that we can see why that is the case. So that's quite a satisfying place to end up. You know, that we've managed to show this all from first principles in our assumptions of what an ideal gas is, and then applying, well, our classical mechanics to it. You know, that was one of the assumptions of the ideal gas, that we could analyze it in terms of classical mechanics. So yeah, we've really completed the circle on all of this, and finally got that theoretical underpinning to something that has been critical to the explanations throughout thermodynamics. All right, so that brings us on to one other thing that is worth mentioning before drawing a line under our first foray into thermodynamics, and that's to talk about the distribution of the particles in the gas, because one of the things which is you've got these averages here. You've got this average of the square of the speeds, and that leads into what's the best way, how do we describe the average particle in a gas, and how do we describe the spread of the particles and in terms of their energy and their velocity around that average. You know, how are we describing this? You know, that's taking a step into the world of statistical mechanics, which is something that we're not going to be studying. So this is sort of how far I'm going to be taking all of this, but we're getting into statistical mechanics. And the key part of all of this is the Maxwell-Boltzmann distribution and the RMS speed. So these are, here we got James Clerk Maxwell, obviously really known for his work in electromagnetism, but the guy was a genius. He worked all over the place. And Ludwig Boltzmann. So the two of them, they derived this distribution independently from each other. So it's named after both of them. And this is the distribution of energies and velocities of particles in an ideal gas. So say we've got an ideal gas. One of the assumptions that we made with ideal gases is that all of the particles in the gas are moving randomly. So they're going to have a range of velocities, both in terms of magnitude and in terms of their direction. You know, they're just moving any old way. So if we were going to draw out a graph of the distribution of, this is like the number of particles is a probability graph versus speed. So let's not worry about directions and things, because they're going to be moving, you know, all directions are going to have the same number of particles. You know, everything's distributed evenly in all directions of motion. So let's just look at the speed and then how that is varying. Now, with Maxwell and Boltzmann, they worked out the exact shape of this particular probability distribution. You've got one of these sort of bell curve setups. You know, you get the idea. It's a little bit wonky. With this tail going off to the right here at higher speeds. So you've got here, well, the higher the curve is, the more particles that you've got moving at that particular speed. So at the peak, you've got here, this is the most probable speed. So that is our most probable speed, but you've got particles that are moving faster than that. You've got particles that are moving slower than that, you know, depending on where we are. You could also work out the mean speed on this. Now, the mean speed isn't necessarily the most probable speed. You know, the mean speed, particularly as you've got this tail going off to the right here, where you can have very, very high speeds, quite often the mean will be off to the side. It might be at a higher speed. So you could have the mean speed there, say. Now, of course, we're not doing mean velocity because the mean velocity is necessarily going to be 0. Because if everything is moving completely randomly and you add them all up and of course, you've got negative velocities, all directions are equally likely. All those velocities are just going to cancel out. That's what happens with vectors. But if you're doing the speeds and we're taking the magnitudes of all those velocities, then you're going to get a mean speed. So that's one setup that you've got. Now, of course, this distribution is going to depend upon the temperature. So that's going to be at some temperature, say T1. If you increase the temperature, because we know that the temperature is related to the mean kinetic energy, that's what it's measuring. So if you've got a higher temperature, you've got a higher mean kinetic energy, which means you've got a higher mean speed. So you're going to end up getting, there's more energy kicking around, you're going to get a flatter distribution, which is, so that's meant to be a bell shape again. It's just me trying to draw these things. So that will be at a higher temperature. It's spread out. You've got a greater range of speeds, which of course means it's got to flatten out because you've got to have the total number of particles being the same if this is the same gas that you've just heated up. So Maxwell and Boltzmann, they derived the distribution, the shape of this distribution, in order to say, well, what's the probability that we've got a particular speed for a particular particle in a particular gas with a particular temperature. So that's what they worked out. That's a first step into statistical mechanics if you can work out that probability distribution. Now, there is, I've marked on here this most probable speed and this mean speed, but are these the speeds that we're really interested in? And is in the title here, I'm talking here about the RMS speed. So this is the root mean square speed. Now, this is another speed, which turns out to be the one which is far more interesting. Now, the reason this one is more interesting, let's go back to our PV equals 1/3 of nm, and then the average of the square of the velocity of the particles in the gas. Now, we're interested in describing gases according to their temperature, and the temperature reflects the average kinetic energy. The average kinetic energy depends upon, well, it's proportional to the average of the square of the speeds. This is what we've been looking at already in the previous derivations. That's what we're looking at, and the temperature is proportional to the average kinetic energy. So these things are all proportional to each other. So when we're talking about the speed of the particles in the gas, and we think, okay, what's the best way of describing this? Well, if we're describing gases in terms of temperature, then the speed that we're going to want to use isn't the most probable speed, and it isn't the mean speed, because that would just be C with a bar on top. We don't want that. We want to get the square root of the mean of the squares of the speeds. That's what we want to do. So that is the root mean square. You've got the root for the square root sign, you've got the mean for the mean sign, and you've got the square for the square sign. So this is our root mean square. And that is the description that we use for the speed of the particles in the gas, because it's the one that is directly related to temperature through the kinetic energy. You can see this path here. So this ends up being a better description of how the particles in the gas are moving around than going with the mean speed. We might have another one up here where we might say, well, this is our RMS speed at a higher speed than those. And we can see that these things are different values. I mean, say we had just 4 particles. Say they were moving with speeds 1, 2, 3, and 4, for argument's sake. Well, if we average those out, you add them up, we got 10, you divide by the 4, so our C bar is going to be 2.5 for that. But then if we're doing an RMS speed, so we've got to square each one of them, so we've got 1, 4, 9, 16, Then we got to average them. So that's going to be 30 over 4. So when you add them all up, we've got 30, divide that by 4. Then we need to root it. So that is going to be root 30 over 2. So root 30 over 2. Well, that's more than 2.5, isn't it? Because root 25 over 2 would be 2.5. So this is greater than. So we're saying that the RMS speed here is greater than the average speed. So it is different. But there's a reason for using it. And sometimes it can be easy. You see so many descriptions when people start talking about these ideal gases and they say, oh, here's the RMS speed of the gas. And I said, well, why are we using that? Why are we going through this convoluted approach to working out an average of having to square everything, then average everything, and then square root everything? What's that all about? Why are we making such hard work for ourselves? Well, it's for good reason. Yeah, I mean, there's bound to be a good reason. You're not just going to do this on a whim. And it's because of this connection of the RMS with the, well, not the RMS, just the mean square. So the MS speed, the mean square speed, that is what's linked to the kinetic energy, which is what's linked to the temperature. So that's why we're using that. So when you get into then doing statistical mechanics, if you decide to go that way, and a lot of people don't. I mean, I did my physics degree. I didn't do any statistical mechanics. So you don't have to end up doing this. It's one of those things that ends up being optional. There's so many different ways you can go through physics. You don't have to be doing thermodynamics as a specialism. But if you do, this is where you're going to start looking at these distributions. You're going to want to be able to derive the Maxwell-Boltzmann distribution. You're going to want to then be able to apply that to ideal gases. You're going to want to be able to look at, well, how, if you've got a gas that isn't as ideal as you'd like, we spoke about this earlier on, didn't we, with the assumptions of ideal gases. What if it is more molecular? We didn't want internal structure really in these gas particles. It's great if you've got monoatomic gases where you've just got a hydrogen gas, say, and you've just got atoms going around. Things start drifting more and more away from the ideal gas, the more internal complexity you're putting into the gas particles. So how much does that start drifting away from your Maxwell-Boltzmann distributions? Are you not getting this same, you're getting significant errors coming in by not being that ideal? And then you're describing things in terms of root mean square speed, which is another way of taking the microscopic and then describing things in the macroscopic. You've got a microscopic underpinning in the fact that you are actually taking all of the individual variations in speeds into consideration. Okay, you're doing it in a statistical manner by applying your Maxwell-Boltzmann distribution, but you're still taking it into account. But then you're managing to then calculate in your RMS speed a macroscopic property, which is then related to temperature, which is, of course, another macroscopic property. So it's just another way, as we have done all the way through these thermodynamic videos, of showing how you can tie the microscopic and the macroscopic together in lots of different ways. No more so than what we had on the previous slide of saying that average kinetic energy of a particle in the gas is that 3/2 kT, something that you will use loads in your calculations in exam questions. It's such a simple yet powerful relationship between macroscopic and microscopic properties of substances. So that's our first foray really through thermodynamics. This has taken it pretty much to the limit that I think is worth going into before you head off to university, but it has stretched it beyond what you normally do in a standard A-level approach to this topic. So hopefully that's been helpful.